Hello everyone. The last class we learned the system voltage regulation measures and understand briefly about the power system regulation equipment. Then we today to study them in detail. First is the synchronous generator. Synchronous generator is the most important reactive power compensation equipment in the power system, often in accordance with different system conditions and different installation locations. Choose a different generator rated power factor according to the need. Generator units located near the load center should have a relatively large capacity to deliver reactive power, which can supply part of the reactive power, the demand of the normal load, but also retain a part in the normal time as an emergency reserved for accidents, which is very important. As is for the generating units of the power plants at the sending end, especially the remote power plants, due to the principle that reactive power is not appropriate to be sent far away. The reactive power it sends out is mainly used to compensate for part of the reactive power loss of the distribution lines during heavy loads to realize the layered balance of reactive power of the ultra-high voltage grid. The power factor is generally relatively high. For example, in the Itaipu hydroelectric power plant in Brazil, 9765 MW units are connected to the AC side of the 900 km. 765 kVAC line to the receiving end, and the rated power factor of the units is selected to be 0.95. The other unit is connected to the receiving end via a DC line, whose rated power factor is chosen to be 0.85, because the former only needs to compensate for the line, while the latter also needs to compensate for the reactive power of the converter station, whose reactive power demand is quite large. On the other hand, the generating units connected to the UHV grid, especially those located in remote areas, need to have appropriate leading phase operation capability, enabling them to absorb part of the excess reactive power of the distributed UHV lines during the low load period of the system, so as to keep the power plant delivery voltage from exceeding the standard. The second is transmission lines. Transmission lines can both generate reactive power due to the presence of distributed capacitance and consume reactive power due to series impedance. When a certain fixed active power is transmitted along the line, and these two reactive powers on the line balance each other, this active power is called the natural power of the line. So lines with high active currents have high reactive power consumption and naturally produce less reactive power. No-load lines are also most likely to contribute to reactive power, which lifts the voltage. Third is the transformer. Transformer is a device that consumes reactive power, in addition to no-load reactive power losses when transmitting power, but also generates reactive power losses through the series impedance. According to what we said earlier, through the transformer, to transmit a large amount of reactive power should strive to avoid in operation when the transformer short circuit impedance is large. It should be more, so the voltage drop generated by the power transmitter through the transformer can be compensated for by appropriately selecting the voltage taps of the transformer. Transformers are divided into three main categories: power supply transformers, power plant step-up transformers, and grid interconnection transformers. Power supply transformers not only provide active power to the load, but also often provide reactive power at the same time, and generally short-circuit impedance is also relatively large for the transformer to directly supply power to the load center. Should be configured with load regulating taps under the premise of realizing the reactive power, zonal and local balancing, with the increase and decrease of the regional load chains. Cooperate with the regional reactive power compensation equipment. The switching of shunt capacitors and low-voltage reactors is carried out to ensure the quality of the supply voltage to the users at all times. whether such transformers should be used with the automatic regulation of voltage taps. There is no uniform practice in the international community because the role of automatic voltage regulation of transformers is not always positive. If the system reactive power, the deficit is very large, the voltage level of the load must also be maintained, and the voltage regulating taps will inevitably transfer all the reactive power deficit to the main grid, which may cause serious system accidents, such as December the 19th, 1978, the French blackout, December the 27th, 1983, the Swedish blackout, and July the 23rd, 1987, the Tokyo system blackout in Japan. The cause of these accidents are directly related to the power supply, transformer automatic voltage regulating taps. Essentially, the reason for this is that it's only an indirect measure, but it doesn't change the balance of reactive power demand in the system. Whether or not a generator step-up transformer is equipped with voltage taps and load-regulating voltage taps is not conclusive. The generator itself is already a very convenient reactive power regulator, and there is no particular need for a step-up transformer to be equipped with voltage taps. Main grid interconnection transformers are characterized by their large capacity. When researching whether this type of the transformer should be equipped with load-regulating voltage taps, there are two features to be considered. Firstly, the layered balance of reactive power compensation and regulation capacity determines that as an interconnection transformer connecting two main power grids, in principle, it should not undertake the task of exchanging a large amount of reactive power between the layers, and the voltage change caused by the change of active load is relatively small. Secondly, in general, since the connection is to the main grid, the level of short-circuit currents on each side of the transformer busbar is quite high, and will be much higher than the capacity of the transformer itself. The voltage taps of the regulating transformer have lost their effectiveness in regulating the busbar voltage. Fourth, shunting capacitors. Shunt capacitors have been widely used in lower voltage supply and distribution grids and uses, also known as low capacitance, used to supplement reactive power. The biggest feature is cheap and easy to install and maintain. Internationally, major power systems are increasing year by year. Most of the shunt capacitors are used to control the load power factor. There are also some connected to the third side of the main transformer as a measure to regulate reactive power compensation. The performance drawback of a shunt capacitor is that its output power decreases quadratically as the bus voltage decreases, which at low voltage can lead to a vicious cycle. The fifth is the shunt reactor. Shunt reactor is a device that absorbs reactive power. 500 kV line is directly connected to the line, called high reactance. It can limit the frequency and operation over voltage, avoid self-excitation, and cooperate with a neutral reactor. It can help UHV, long-distance lines, in the single-phase reclosing process, be easy to arc extinction to ensure the success of single-phase reclosing. 220 kV line is generally installed in the transformer winding third side. It's called low reactance. 6. Series capacitor, also known as series compensation, are used to compensate for part of the series impedance of the line, thus reducing the reactive power loss when delivering power, and thus are also a kind of reactive power compensation equipment. But series capacitors are more widely used as an important measure in power systems when transmitting power over long distances, improving system stability and power deliver capacity. The value QXCV of the terminal voltage promoted by series capacitors, that is, the regulating effect increases with the increase of the reactive load and decreases with the decrease of the reactive load, which is exactly the same as the requirement of voltage regulation. This is a significant advantage of series capacitor voltage regulation. However, for lines with high load power factor, cosine phi over 0.95 or small conductor cross-section due to the large proportion of PRV component, the regulating effect of series compensation is very small. There are also some difficulties in using series compensation in high-voltage systems. Firstly, the complexity of the compensation station itself requires to be able to put the series capacitor back on and the protection of the series capacitor itself after the fault has been removed. The second is the difficulty of relay protection. Conventional distance protection for series compensated lines encounters some special problems. The third is to solve the problem of subsynchronous resonance that may be arising from the series compensation line of the turbine generator unit distribution. The seventh is the synchronous condenser. Synchronous condenser is the earliest use of reactive power compensation equipment, now mostly not used but to adapt to the grid stability and the need for DC transmission. In some cases, still has its specific role. The eighth is the static compensator SVC. The static compensator consists of a power capacitor and adjustable reactor connected in parallel. The capacitor can emit reactive power, and the reactor can absorb reactive power. According to the need for voltage regulation, the adjustable reactor to absorb the reactive power in the capacitor bank to regulate the magnitude and direction of the reactive power output by the static compensation. The static compensator can quickly and smoothly regulate the reactive power to meet the requirements of the reactive power compensation device. This overcomes the shortcomings of capacitors. As reactive power compensation devices that can only be used as a power source but not as a load and cannot be continuously regulated. However, it is also not applicable in a grid with a very weak receiving system, because its capacity will decrease quadratically with the drop in bus voltage. In a sense, the static compensator is primarily a reactive power regulation measure with rapid response. Compared with the synchronous condenser, although the cost is comparable, the static compensator's regulation is more rapid, which is an outstanding advantage, and to be able to utilize its reactive power, rapid regulation capabilities when needed. As for the voltage changes caused by normal load changes, the process is relatively slow. Using the general much cheaper, capacitors and reactors can fully meet the requirements. There is no need to choose this high-performance equipment. Therefore, this method is generally used for nodes with large load shocks, voltage hub nodes, two sides of the contact line where the power is easy to fluctuate, and emergency backup nodes for accidents. Well, class, that's all for today's lesson. See you in the next class.